All right, so Echem 1, what we're going to talk about is we're going to talk about galvanic cells. Those that are thermodynamically favorable and will run on their own without outside intervention. We're going to talk about what voltage is and the electrical cell potentials for a battery. You know, like a battery is a 9-volt battery. The electrical cell potential for that battery is 9 volts. Okay, so that's what we're going to talk about. So what is even an electrical current, though? So current is equal to, and if you look, okay, don't freak out. This is on your formula sheet, okay? And we're going to do some work with this again tomorrow. But current, this is the last formula on the formula sheet. The one above it, actually, we're doing tomorrow. But by tomorrow, you'll know all the formulas. So current is equal to Q, which is the charge, in coulombs. So electrical charge is in coulombs. And, you know, you can look to the right-hand side, and you can see that Q is equal to charge, which is coulombs. See? Don't freak out. It's on your formula sheet, right? Are you matching it up? And this divided by time, and time has to be seconds. And it says that on your formula sheet. The only thing that's not on your formula sheet is the fact that amperes is coulombs per second. And you have to know that. So, I don't know if you remember, like from apes, watts were joules per second, and you couldn't really use watts for anything, so you had to go to joules per second. It's been a pop for some of y'all, but that was a thing. Anyway, amperes is coulombs per second. So anytime you see that capital A, you have to convert it to C over S, and then you use it as a conversion factor. You know how I tell y'all to do dimensional analysis and you don't start with something on the bottom of the fraction? Like you would never want to start with something, if it was like 18 amperes, you would never start with 18 amperes. That would be a conversion factor at some point to get you to coulombs in seconds. Okay. So just go with it. And then coulombs again is the charge. And if you look on your formula sheet, Faraday's constant is there. So as far as charge is concerned, there are 96,500 coulombs in a mole of electrons. So this is just good, solid dimensional analysis, which I like. When I went and audited this class to kind of get this part down, I really struggled with everything we just learned recently. But when we got to this day, it was dimensional analysis, and she was teaching, and I was just like, slash, 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 done. And so it was great. So this is fun. If you've ever had any other class with me and I've made you learn dimensional analysis, you're good. So we're going to come back and do some more of this tomorrow, but these first two questions are pretty straightforward. So check it out. Just like anytime you're doing dimensional analysis type questions, how much charge passes through the cross-section of a wire that is carrying 0.987 amperes? So that's 0.987 coulombs per second. And then I like to draw these little boxes for conversion factors. I've been doing this with apes this last 2 years. I think it's good. And then that's for 12.3 minutes. Minutes doesn't have a buddy. So if I start, I'm trying to get charge, which is coulombs. So I circle it. I want that in the top right-hand corner. So 12.3 minutes. And I told you that, you know, coulombs per second was a thing. So I'm going to go ahead and go to, you know, 1 minute is 6. Oops. Okay. 1 minute is 60 seconds. And then notice I can now use my ampere conversion, 0.987 coulombs per second. And charge is coulombs. So if you just punch buttons in your calculator, you'll get the answer to this. So 728 coulombs. And then that second question was asking how many moles of electrons. Well, if you have coulombs and then you look at Faraday's constant, 1 mole of electrons, and your formula sheet I think has, yeah, it's rounded. It's 96,485. On the AP exam, you want to use 96,485, okay? But 1 mole of electrons is that many coulombs, and then you're done. Tomorrow, we will do like electroplating. It will be this, and it'll just kind of have more steps. But if you can do dimensional analysis, it's fine. To be real honest with you, this kind of went the way of the energy is, you know, wavelength and all that stuff at the time, kind of real straightforward math. They don't really ask a lot of questions about this anymore, but it's still in the formula sheet, so it could be a thing. But, you know, since it's easy, no, right? All right, so redox reactions. We've been talking about this for a couple days. This is actually the same reaction that we just looked at the galvanic cell. With the zinc is going to be our anode, and then if you see here, the zinc is going to lose 2 electrons. The electrons are going to go to the copper, and the copper is going to go from 2+ to actually being a charge of 0. So the copper is going to get reduced. So this is it. Okay. So what you're going to have to be able to do is we have to be able to take a redox reaction. They're going to give you a reaction, and you're going to have to figure out what the reduction half reaction is and the oxidation half reaction is. So I want you to take a second and split this up into a reduction half reaction and an oxidation half reaction. And if the electrons aren't balanced, then you'll need to do that, but I think they are balanced. So I'm going to I guess I can kind of just scooch over here. I don't like to skip steps. So we can see that copper is reduced and zinc is oxidized, right? And then you have to write the word oxidation, right, and show me that reaction. Oops. What you're going to do as you work with these is you're going to be tempted to write -2 electrons. It's never minus electrons, okay? It's always going to be plus electrons. So when you write the half reaction to get those electrons to see if they need to be worked on to get balanced, you need to think about the overall charge of the reactants and products. And so here I can see the overall charge of the reactant side is 0 and the product side is 2+. I can't add protons. So the only way to balance these charges is to add 2 electrons. So if you kind of can follow that pattern, you add electrons to the positive side. That's how it goes down, okay? Full over. But you don't subtract electrons. I've seen it too many times on paper, so I don't think it's cute either. So anyway, zinc plus 2 electrons. I ran out of room. I would have liked to have continued writing it off to the side. And then the reduction half reaction. Copper, 2+ plus 2 electrons, right? Gives me copper as a solid. So those are my 2 half reactions. Because the electrons are the same in the reduction and oxidation, I don't need to do anything as far as multiplying one of them. And then when you go to add them back together, you do get the same overall reaction. On the AP exam, it's not going to work out like that. They're going to give you a reaction. You're going to have to split it into the reduction and oxidation. You're going to have to balance the electrons, and then you got to add it back together. Like that's the first 3 points on your final. It's the first 3 points on pretty much every test. You've seen these battery questions at the beginning of every release exam as you scroll through. This is it. Okay. So anyway, when you add them back together, you do get that, but that's not always the case. Not like what they give you to start with is not always what you end back up with after you balance your electrons. Just in this situation it was. All right, so if I had a copper penny and I drop it into silver fluoride, this is the reaction they would give you. So what you have to do now is you have to write a balanced redox, a balanced redox reaction. So you would do that by splitting it into the reduction half reaction and the oxidation half reaction. So I want you to do that. And I want you to give me the same number of electrons in the reduction as in the oxidation, and then add them up together. And I know this is easy and some of you can just look at it, but the ones on the AP exam are not easy and you cannot just look at it. So you need to practice while it's easy. pen's being weird, so I can't write over this anymore. I was trying to be efficient. Anyway, I feel a need for me to work this out for you. Copper. I just need to take a picture of it, I guess. These get hairy really quickly, so make sure we got it when it's easy. Alrighty. Oh, I've broken my pen making an effort to use the squared off shapes. Sad face. Let me get out of this and just draw a line. Well, yeah, I think I just want lines. Is that going to draw some weird line? Looks like it. Okay, I think that's the answer. Alright, cool. Okay, now we're in business. When I'm splitting up the reactions into the oxidation half reaction and the reduction half reaction, I honestly split my paper in half. And you'll see, you'll appreciate why I'm doing this later, in about 5 minutes. So when I go to combine them, make sure your electrons are the same on both sides. And then you have copper solid plus 2 silver ions gives you 2 silvers and copper. Is that what you got? We have the same sweater on. How did we not notice that earlier? It's okay. You're a cool kid now. Outside. Oh no. I'm sorry, sweater. Okay. So there's that. How do you feel about it? Now, look, they just magic fairy this answer up here. And you can do, listen, I know you can do this in your head. I know you can. I know this is not hard, but I know it gets hard. Just go with me. I got your best interests at heart. Like, I got you. Look, I know where we're going. I've been to this party. So again, galvanic cells are always spontaneous, so gives free energy is negative. Electrons are going to transfer from one reactant to another. And so we just saw that outside, and that's electrical energy. Now this is terrifying, right? When you just look at these pictures, they're super scary, but this is what we just did. So this is where I want y'all to rewrite the N-old cramp to make sure you got it. So N-old, then over here I have cramp. And so I have the anode. It gets negative ions from the salt bridge. This is where oxidation happens. It loses mass. It donates electrons to the wire. Be careful that you don't accidentally say, like, donates electrons to the, salt bridge or something. Be careful with that. This goes to the wire. This is the cathode. Reduction. This is accepts electrons from the salt, accepts electrons from the wire. The mass increases, and it gets positive ions from the salt bridge. So this morning, I haven't looked at this in a solid 8 months, and I remember this, like that. I mean, yeah, I made it up, but it's easy to remember. Alright, so, like I said, these pictures are kind of scary, but let's look at them. So zinc is a solid metal. Zinc is going to lose electrons, which is why it has a 2+ charge. As these zinc ions increase, that's why the negative ions need to come into solution here to bounce a charge. The electrons are going to go from the anode to the cathode. They will build up a negative charge in the cathode, this piece of copper. And the negative electrons will attract the positive copper ions. And then copper solid will build up on the cathode. How does that make you feel? Should feel pretty good. Over time, this will lose mass as more zinc ions go into solution. And up here, we'll run out of those copper ions. And that's when the battery goes in. Yay. And we'll do some mathematical kind of discussion of that tomorrow. All right, so we've already done this 3 times. The anode, you see the ions kind of come off as the solid metal loses electrons. And then over here you get more solid as the cathode gains mass from the ions getting the electrons and becoming solid. The salt bridge, typically you'll see those, typical spectator ions, sodium, nitrate, sulfate sometimes. Those are like sodium nitrate is like probably the most common one. So anyway, last year when I did this, I spent $27, and that's really the amount of money on a salt bridge, like a gel U-shaped piece of glass that has like a porous gel in it. I spent the money on that, and then I soaked it like you're supposed to. And it didn't work, and so then I went on the discussion board, and I was just like, this doesn't work. And they told me to take a piece of filter paper and put it in, and it did. And so it just has to be porous, like it just has to be able to transfer ions from one side to the other, and it doesn't have to be anything fancy, but it did not work without it. As soon as I got that filter paper and put it in, it started running. It was really cool. I'll set one of those up in the morning and let it run, and I'll actually take the mass in the morning and at the night, and you can see that the cathode gets heavier and the anode gets lighter. I just went through the anode cramp in my head. So anyway, salt bridge, anions go through toward the anode. Oh, that's good, anode. That's cool. But the negative ones need to come over here because we start to get that influx of positive ions as they are oxidized. And yeah, so anyway, cations go through the cathode, and that's because I need the positive ions to replace the copper that turns into a solid, goes from a 2+ to a 0 charge as it is reduced. Alright, so why do they flow? Electrical potential, that's why. So this isn't really helpful to me. These batteries, can I just tell you, let me just make this easier. These batteries, these galvanic cells, you should call it a galvanic cell, they're the amount of voltage they have. Voltage is like density, okay? Let me explain it like this. Voltage is like density. And what I mean by that is if I have a tiny piece of gold or a giant piece of gold, the density doesn't change. So the voltage of a battery, like if I had a 9-volt battery, like it doesn't matter if that 9-volt battery is this big or this big, the voltage is still 9 volts. Now, you can think about it like a waterfall too, which is why I'm just gonna, this isn't a waterfall, but that guy's at the waterfall. Anyway, that electrical cell potential, if it's 9 volts, then it's 9 volts. And if I increase actually like how much is flowing through there, that's amperage. But this is physics and you don't need to know that. But you do need to know that if I double a reaction, you know how like we have to double stuff to get the electrons to balance? If the electrical cell potential is 0.2, like it doesn't get doubled to 0.4. It stays 0.2. It's like the height of the waterfall. It's not how much water is flowing, it's the height of the waterfall. If you want to double it, that would be amperage. And like I said, we don't have to deal with that. So if you can remember not to change the voltage because it's an intrinsic property, there's some that you don't change, like density. Doesn't matter the amount. Is that right? Thank you. I love you. Thank you. So all this is voltage. Basically, we're going to be dealing with voltage, okay? So the driving force that causes those electrons to move is the electromotive force, EMF. That's standard with the little knot symbol, right? Electrical cell potential. So like this is what we're going to be working toward. When you see that little zero symbol, this is just like thermodynamics standard state where it's 1 atm, 1 molar, 25 degrees. Oh, okay. Well, whatever. So we're going to be working with this. The AP exam does not expect you to work with things that aren't at standard. So, yeah. Anyway, you can, what they will want you to do is make a Q versus K statement. Yay. But mathematically, they took out the equation from the formula sheet, the nurse equation, to mathematically be able to solve what will happen if the battery's at a certain point. So we have to make Q versus K statements, and I'll show you how to do that. It's the whole number line thing. Okay. Make sure I'm numbers. Yeah, me too. Anyway, so 1 molar, 1 atm, 25 degrees Celsius. So check it out. Here's the deal. On the old release exams, as you're scrolling through, did you see like giant lists of this? You ever seen this before? Have you ever studied for a test? Okay. Just saying. These electrical, the electrical potentials, they are given as reduction potentials. So that means in that giant list, all of these are reduction reactions. And you can see here that they all gained electrons. There's no oxidation up here. Now, if we have a battery or we have a redox reaction, are both reactions going to be reduction? So if I take this reaction right here, this copper 2 plus 2 electrons give me copper. If I reverse that, guess what kind of reaction it is? Oxidation. Now, I will have to make this negative 0.34. If I multiply it by 10, though, like if I had 10 electrons and I had if I multiplied it by 5 to get 10 electrons, I would not multiply that by 5. That waterfall is not any higher. It didn't change the density. Same idea. Okay. The coefficients matter to balance the electrons to get the correct overall reaction. You just still have to do that. I'm telling you that, you can just add, you end up basically adding them up. I don't like those little shortcut things. They're about to do some shortcut stuff. I'm not about that life. I can't do it. But I'm going to show you a really easy, way to do it that won't make you in a week go, what was the formula that doesn't exist again? If it ain't on the formula sheet, I'm not trying to show you, because then you won't remember. So, anyway, going back. So, this is the reduction potential of copper. And it's positive. So, that means it would be thermodynamically favorable, because it would release 0.34 volts, which would be free energy. Right? And if it's releasing free energy, it gives free energy is negative, and this would happen on its own. A 9-volt battery ain't negative 9 volts. It's positive 9 volts. Positive 0.34 volts. That's the thing. Got it? That's life. Alright, so this is honestly what's going to happen. They're not going to give you oxidation potentials. That doesn't exist. Okay? So on the AP exam, this is very common. They'll give you a list of reduction potentials, and they'll ask you to write a redox reaction for a cell made from iodine and copper. Okay? Iodine and copper. They'll give you the reduction potentials, and then you have to design the cell. Well, that sounds really hard, right? It's not. So if I told you, let's think potential for going to college, okay? If I told you your potential for going to college is 0.77, but somebody else's potential for going to college is 0.53. Well, which one of y'all is going to college? 5.77. These are reduction potentials. The one with the highest reduction potential is the one that gets reduced, and the other one gets oxidized. Now that makes sense. It sounds real cool when I say it, yeah, that's easy. I'll catch you in a week. Let me know. So let's just make sure you understand this, because it throws people off. I don't know why. Let's say that I was designing a galvanic cell with nickel, this nickel, and copper and nickel. These two. See it? Talk to your little friends and figure out which one of them is going to get reduced, which is the half reduction. Because copper, right? You understand? You know how sometimes I pause like this because I've already seen what happens with people? I've already seen how this goes down. This is super simple. I can't make that any simpler. But I'm not always with you, talking to you, making you feel better about it. So, you got it? You sure? All right. So, which one's going to be reduced? The one with the highest potential to get reduced. I don't like this. We're not doing that. All right, so check it out. You're about to have to design a galvanic cell. Galvanic and voltaic is the same. I feel like the AP exam uses galvanic. It doesn't use voltaic. It doesn't matter though. What is the cell potential for a voltaic cell that has a nickel at one electrode and copper at the other? Ooh, they didn't even tell you which one was which. Isn't that nice? The cells are kept at 25 degrees Celsius and ions are 1 molar. So that tells you that you can use these standard ones because that little dot or that little not sign means that. Okay. So the first thing you have to do is you have to figure out which one is going to be reduced. So which one of these is going to be reduced? Anybody? Just, are you sure? All right, cool. So let's take this over to the other board, and what we need to do, and I don't care what this question is asking. I'm telling you what you're going to have to do. They're going to do this to you. Then they're going to ask you to write the half reactions. Then they're going to ask you the electrical cell potential when you add them up. And they're going to ask you to give the overall equation. Okay, so let's do it. I'm just looking at my pictures because I already took a picture of the screen. I'm going to do this one for you, and then after I'm done, there's one just like it. So, anyway. I think this is it. Yeah, this is it. All right, so I'm going to split my paper up. We just said that copper is going to be the one getting reduced, and the reason it's getting reduced is because it has the highest reduction potential. It has the highest potential to be reduced. Can you hear in my voice how many times I've had to say that to people after they mess it up? Can you hear? So the reduction half reaction is, as written, the copper 2 plus 2 electrons gives you copper solid. And then the oxidation reaction, I'm going to have to, and then the electrical potential is equal to 0.34 volts. Okay. The oxidation half reaction, I cannot write it as written. I have to reverse it, and so I'll have nickel as a solid goes into nickel as an ion, 2 plus 2 electrons. And the electrical cell potential, or not electrical, the cell potential is the whole thing. This is the electrical potential of this part is going to be positive 0.25 volts. Are you good? Okay. At this point in your life, you have to make sure the electrons bounce. Do they? Cool. So I don't have to multiply anything. So now that I have my two half reactions written in the correct order, I can just combine them. Okay. So I'm just going to start over to make it a little bit easier to follow me. Okay. And now to get the electrical cell potential, the standard electrical cell potential, it's going to be 0.59. How does that make you feel? That ain't that bad, right? Now, if I had to multiply this by 2, if I didn't have to, but if I did, if I needed 4 electrons or whatever, I would make this 2 nickels and 2 nickels and 4 electrons, but this number would not change. You can flip it around when you reverse the reaction, but you don't change how tall the waterfall is. Anyway, you don't need me to go back. What happened? Yeah. want you guys to I want you guys to do this one. Is this class almost over? Okay, so give this one a try. Or we can just wait till... I think it's actually time to go, right? Yeah, so we'll finish this up tomorrow. We have class tomorrow, so it's no big deal. We're good. But I do that.